Hi, and welcome to this walkthrough and quick review of chirality in pharmaceuticals in the form of an exam question. So I'm going to use the exam question as an opportunity to do a quick review of some of the ideas it's covering as we go. So it also mentions chirality. So quickly to recap, this includes 4 different groups that must be on the same carbon atom. So you can see there's a yellow group. I'll just take my highlighter, yellow group, green group, red group, and purple group. So they can be as small as one atom, or they can be as large as a whole section of molecule. So what happens is this gives rise to 2 optical isomers, and these are called enantiomers. And from the animation you can obviously see that they can be thought of as non-superimposable mirror images. So the way they'll question you on this most commonly is to spot chiral carbon atoms in complex pharmaceutical molecules, for example like this steroid. So the way to do this is to come at it from the other way, to find the actual carbons that obviously couldn't be chiral. So you need to find carbon atoms that have more than one of the same atom bonded to them. That means they're not chiral, and then by default the ones that you don't choose must be the ones that have 4 different groups attached. So let's have a look at all the carbon atoms that have double bonds, because that means that the carbon is bonded twice to the same atom. So they can't be chiral. Next up, anything that's a CH2, so a carbon with 2 hydrogens bonded to it. So you'll see there's quite a few of those as well. So quite quickly you'll be able to whittle down your options. So it's easy to spot a CH3, obviously that's going to have 3 hydrogens attached to 1 carbon. So that must mean that the remaining sites that have carbon atoms mean they're chiral centers, as we say. So if we remove all the ones that aren't chiral, that reveals the chiral carbons in this particular structure for us. So it says enalapril is a drug used in the treatment of high blood pressure. They want you to mark each chiral center with an asterisk. Thankfully it's quite straightforward. It's not as involved as the previous molecule, although the previous molecule did come from an A-level paper. So checking the mark scheme, we can see that where we've put our stars matches where they've put theirs. So the next part of the question is about acid hydrolysis. So I'm just going to quickly take you through acid and alkaline hydrolysis of amines. So taking an acid hydrolysis initially, using heat and reflux and the aqueous acid, the amide functional group is hydrolyzed into carboxylic acid and ammonium salt. And if you take a alkaline approach, same reagents and conditions, or same conditions rather, but the reagent this time is NaOH, or a similar hydroxide. You'll have a carboxylate ion this time round, which will form a salt, sodium carboxylate salt this time round, and an ammonia molecule, or if it's the amide is primary or secondary or tertiary I should say, it's going to be an amine that is formed instead. So the next part is where enalapril is broken down in the body by acid hydrolysis. They want the structures of the 3 organic products with the acid hydrolysis of enalapril. So firstly you look for an amide functional group, and obviously that's where the reaction we've just considered would take place. But there's 3 organic products, that would just make 2. So therefore we need to think about elsewhere in the molecule that could be susceptible to hydrolysis. So there's an ester functional group up at the top there, and under acidic conditions and heat that would also hydrolyze. And then finally the secondary amine functional group in the middle of the molecule would be protonated by the acid in the acid hydrolysis. So let's have a think about what that might make. So firstly, the ethanol molecule comes off and a COH group forms. Then when you protonate your nitrogen on the amine, you'll get an ammonium ion with the protonated N+, and the rest of the molecule either side. Now notice on the right-hand side, we don't have this part of the molecule anymore, because obviously that's come off when hydrolysis took place over here, and that gives you this structure. So this particular structure is a proline salt. Proline is the amino acid with that 5-membered ring containing the nitrogen atom. Okay, so the next part of the question is about gas chromatography, so I'm just going to quickly review that in conjunction with mass spectroscopy. So as you can see, the mixture as vapor is added at the top, and the orange part is an oven, and you can see the individual components starting to separate and move through the column at different rates. So once they're detected and they're sent through the ionization process of the mass spectrum, in the gas chromatograph, the peak position represents the retention time, and the peak area represents the proportion or concentration in the mixture of that component. So a desktop version of this, you'd have a rotating carousel for storing samples. The samples injected at that structure there, and then obviously your oven is here, and this is going to be your mass spectrometer. And the whole lot is connected to a laptop. Now inside the column, in this animation, you can see the stationary phase is the gel, this yellow stuff here, lining the column. And the carrier gas moving your components through is usually an inert gas such as nitrogen or argon. So the green component in this animation has the greatest affinity for the stationary phase, so its intermolecular forces cause it to interact most effectively with the stationary phase. So you can see the green particles there sticking to the gel. The animation has emphasized this for you. So that means it travels more slowly and has a greater retention time. It spends longer in the column. The blue component, you can see that's not really interacting at all with the stationary phase, because its intermolecular forces would be such that it interacts more effectively with the carrier gas, so it's moving more quickly, and it travels for a shorter amount of time through the column. So the next part of the question, and the final part, asks you to explain how GC-MS enables the products to be identified. So GC is a separation technique, and MS is an identification technique. So to get your 1 mark, that's the kind of thing they're looking for. Okay, as always, thanks for listening. Until next time, see you soon.